Example 4, reading the graph of the derivative. In this example, we're going to be given the graph of the derivative, and we're going to use that to determine attributes about the regular graph. We're also going to use the derivative to tell us about inflection points and how they also affect the original graph of f. At the end of this example, we will be able to graph our original function only given the derivative. This is going to be possible by talking about inflection points and other attributes about increasing and decreasing. So go ahead, take a second, and copy down that graph. This graph represents the graph of the derivative. Do not get this confused with the graph of f or the graph of the second derivative. This is the graph of the first derivative. The first question asks, on what intervals is f increasing? So I kind of scaffold the questions in order to help us understand the graph of the derivative. On an FRQ on the AP exam, they won't give you these questions. These are things you need to know to look for. So, what intervals is f increasing? Well, since f prime of x is greater than 0 on the interval -4 comma -2 and -2 comma 1, it's increasing. And since f prime of x is equal to 0 at x equals 2, we have that f is increasing on the interval -4 comma 1. So let's look at the graph and understand that for a minute, because we're not looking at where the graph is increasing. We're looking at where the derivative is positive. So the derivative is positive here and here. But because the derivative here is 0, it stays positive. So our graph is in fact increasing on this entire interval. Our graph might be doing something kind of like this, but it's always going up. Okay, what intervals is f, not the derivative, but f, concave up? So a graph is concave up when f prime of x is increasing. So f of x is concave up whenever f prime is increasing. So then f of x is concave up on the intervals let's figure this out. So look, right here, the derivative is decreasing because the f prime of x is going down. So here the graph would be concave down, but we want concave up. So this is, here the graph is increasing, then it starts going down again. So we're concave up from -2 to 0, and we're concave up from right here at 3 to 4. These are the areas where the graph is concave up because the derivative is increasing. At what x coordinates does f have a local extrema? At what x coordinates does f have a local extrema? So we know from the first derivative test that f, our original function, has a local extrema wherever the derivative is equal to 0 and the sign changes. So first, let's write that down. So f of x has a local extrema when f prime of x equals 0 and, this is important, and f prime of x changes signs. So this means that not only does the derivative need to equal 0, but it also has to go from positive to negative or negative to positive. So let's look at all the places where the derivative equals 0. So we look at this graph. It equals 0 here, and it equals 0 here. So let's talk about those. When x equals negative 2, this is not a local min, or max, since f prime of x does not change sign. Let's look at the other one, x equals 1. What do you think this is? Is this a local max, local min, or not an extrema at all? Or not an extrema at all? X equal 1 is a local max, since f prime of x goes from positive to negative. Now what we have to do is we also need to look at our endpoints. We need to look at the point right here and the point right here, because those are our endpoints of the graph. So let's talk about x equals negative 4. X equals negative 4 is the left endpoint, and since f prime of x is greater than 0 at x equals negative 4, it's a local min. Now this is kind of confusing, because let's go back up. Here, the derivative is going down. So shouldn't it be a local min or a local max? That's the question. Well, even though the derivative is going down, it's still positive. So what that means is that our function, if this was f, is going up but becoming more horizontal. So it's a local min. Now let's look at the last one. X equals 4 is a right endpoint, and since f prime of x is less than 0 at x equals 4, it's a local min. Now this is kind of confusing, because I said that this one, for the x equals negative 4, the derivative is greater than 0, so it's a min, and x equals 4 is negative, so it's a local min. Isn't that contradicting myself? Well, let's look at some graphs real quick and determine why. So here's a graph, and I want to have a left endpoint. And it says the derivative is positive, so my function is increasing. Well, you can see right here that this is a min. Now let's look what happens if it's a right endpoint. Right endpoint, and it says my derivative is negative, so it's decreasing. Well, this is decreasing, but this is also a min. So it depends if you're a right endpoint or a left endpoint. That's going to determine if you're a min or a max, depending on the derivative. Okay, what are the x-coordinates of all the inflection points of f? So what we need to do then is we need to know that from the graph of f prime of x, we need to look at where the graph goes from increasing to decreasing, or decreasing to increasing. So on f prime of x, we need to look at where the sign changes. These are called the turning points. So let's go on to the graph. We want to figure out where the graph turns around. Well, the graph turns around right here. The graph turns around right here, and the graph turns around right here. This is where it goes from being decreasing to increasing, increasing to decreasing, and decreasing to increasing. So we know then that the turning points on the graph f prime of x are x equals -2, 0, and 3. You can think of this just like when we used the first derivative test. We looked at where the graph's maxes and mins are. Well, the max and mins of a first derivative are the second derivative. So now here comes the really hard part. We need to sketch a possible graph of f of x on the interval -4 to 4. So first of all, we need our minimum value. And our minimum value happens at x equals -4. That's our minimum x value. So it really doesn't matter where we put the y value. I'm going to go ahead and just put it right here. Again, it doesn't matter if it's on above or below the x-axis. That doesn't matter. Okay, the next thing we need to look at is our max and mins. We need to figure out where we have a maximum and a minimum. Well, I'm going to go ahead and I'm going to plot all of these, which are going to be my turning points or my max and my mins. So I have one at -4. I have one at -2. I'm just going to put that right here. I have one at 1. I'm going to put that right here. And I have one at 4. So I have one over here. Now, this is where it gets tricky because you don't know, does the dot go up here? Does it go down here? Does it go down here? You don't know. Well, let's think about it. When we start at our left endpoint, are we increasing or decreasing? At our left endpoint, it's a local min, so we have to be increasing. Also, the graph of the derivative is positive, so we increase all the way to -2. So this means that I'm going to increase all the way to -2. Now the question is am I going to increase this way or this way? So this is where the concavity comes in. Are we concave up or concave down? So let's see. The intervals where the graph is concave up is where the derivative is increasing. So we're concave up from -2 to 0 and 3 to 4. Well, that must mean we're concave down everywhere else. So that means it's going to look more like this. It's concave down. Now what happens at -2? Is it a max or a min? At -2, it's not a max or a min. That means we have a shelf. It kind of plateaus, kind of like x cubed. But does it stay concave up or concave down? Well, it's concave up from -2 to 0. So we go back to our graph. So it's going to go from -2 to 0 and be concave up. So it's still increasing, but it's concave up, something like this. And then it becomes concave down again to get to this point. So it goes something like this. So that the bend of the graph changes. So right here it's concave down, and then right here it shifts to being concave up. I'm not really good at drawing these, but that's my best shot. So let's identify all our points. Right here on the graph. So let's go ahead and let's identify all of our points. Right here on the graph, you have an inflection point. Right here, you have an inflection point. Here we have a local max. Here we have a local min. And here we also have a local min. This is a possible graph for f of x. The graph could look differently depending on where the maxes and mins were. I know my graph's not necessarily perfect, but it's pretty close. If you were to draw this kind of a graph, as long as everything's labeled on a test, that would be okay.